We're now going to go on to topic 3 of chapter 9, logarithmic functions. We're going to look at graphs of logarithmic functions, common logarithms, equivalent equations, and then solving certain logarithmic equations. But we're going to start slow, and for some of you this may be new material. We are now ready to study inverses of exponential functions. Remember, the inverse was where we exchanged the x and the y. These functions have many applications and are referred to as logarithms or logarithmic functions. Graphs of logarithmic functions. Consider the exponential function that we worked with in the previous section. F of x is equal to 2 raised to the x power. Like all exponential functions f, they need to be a one-to-one. That is, as you look at this original function here, does this red line pass the horizontal line test? Just the red line. And the answer is yes. So that is one-to-one. So it would have an inverse function. In fact, this is the graph of the inverse function, with your axis of symmetry being y equals x. And if you fold this diagram along this line and this line would be a reflection. That is, the image would overlap. So, how can this formula from this formula be derived? Well, we'll use the method we talked about in 9.1. We're going to replace the function symbol with the letter y. So we then get y equals 2 to the x power. We're now going to interchange the x and y as we've done here. And now we solve for y. This is the little tricky part. So what is y? We're going to say y is equal to the power to which we raise 2. Y is the power to which we raise 2 to get x. Now, we'll give you an example of that right now. They're doing this down here, but I thought I'd do it right now. So let's say that x now will be 8, and 2 is our base. What power do we need to raise 2 to make this a true statement? And 2 to what power is 8? Well, 3. So in solving for our y here, we're saying that y is equal to the power to which we raise 2 so we can get our x. And that's what we do then. We replace our x over here. Well, I should say our y there with this symbol now. That's F inverse is equal to the power to which we raise 2 to get x, which is what I've described there. And we now define a new symbol to replace the words, the power to which we raise 2, which is a base. 2 is our base here. This is the exponent to get x, which is our results. And the symbol we use to replace it is log base 2 of x. Now it can also be read the logarithm base 2 of x, or I like this shorter version, log base 2 of x, which means this statement here, the exponent to which we raise 2 to get x. This exponent we raise 2 to get x. And they have illustrated that here as well. Let's continue. Now, they give us some examples. And again, what I want to do as I do this with you is I want to give you a technique, a strategy to get to these. So as we look at these over here, remember log is going to be some number of base 2 that will give you a 32. So 32 is what you are looking for. Your base is 2. Now, what will be the log of this, or the exponent that will raise 2 to 32? So, in a sense, 2 to what power is 32? Well, you may or may not know that, but it's to the 5th power. So our answer to letter A is 5. That is the log of this. It's the exponent of the base 2 that will give you the results of 32. So again, I'm strongly suggesting that you set it up in some pattern that you can solve it. So again, what will be our exponent of base 2? That's the exponent up here that will give us a 1. Well, we know that anytime we raise anything to a, except 0, to a 0 power, that will give you 1. So the log of base 2 to 1 of 1 is going to be 0. All right, again, what will the exponent be of base 2 that when we raise it to that power will give us 1/8? Well, again, this relates to other work we've done, but it's going to be a -3. Because 2 to the -3, remember, it just takes this 2 to the -3 becomes 1 over 2 to the 3rd, which becomes 1 over 8. This is from previous sections that you would need to know that. But here we're focusing on how to translate this new notation, logarithmic notation, into what does it represent. Okay? Now, they do give us some other work where they're saying it's not always going to be a nice pure number, so to speak. So if we had something like this one, how would you set that up? Well, once again, we're going to say 13 is our results. We're going to have our base is 2. And then what would the exponent be? And it's going to be 2 to the third is 8. 2 to the fourth is 16. So it's going to be a number somewhere in there between a 3 and a 4. And it actually comes out to about 2.7, 3.7 I should say. So the exponent is 3.7. And you could read this over. So in a sense, when we have our original function notation, exponential notation, the inverse of it, that is this down here, is called log base A of x. That is the inverse statement of what they are saying here. And what the blue line, a blue curve, is. So the meaning of log sub A of x. In this case, x is going to be greater than 0. A positive constant other than 1. Log A of x is the exponent to which A must be raised in order to get x. So, interpreting this, what does that mean? Well, again, it means this, but what does this mean? Well, again, think of an example. If you ever get stuck, just write this little example out. 2 is your base. Your exponent in this formula here is m, and x is your results. So what they say, the log of A. What can we put for the word log? And it's the exponent. Exponent is your m here. M is your exponent. When you put it in log form, there's what we're looking for. So what is the exponent of A that will give you x? The exponent of A that will give you x. A is your base. This is red. Exponent of the base gives you a value, a result. That's what logarithms are. Okay? And here they're saying it again. A logarithm is an exponent. What is a logarithm? The logarithm is an exponent. Say it again. They're telling us repeat it. But again, I think this way is an excellent way. You're going to equate this to this. And you could put here log. So 2 to the log, 2 to the exponent equals the results. All right, let's try some examples. Now for example 2, as we look at it, let's see if we can analyze it a little bit. Here they're saying to simplify this. Well, keep in mind this part right here, which is this, in a sense is, we're wondering for our base 7, what is the log, which is an exponent, that will equal 85. So if they say we're going to take a 7 and raise it to this power, this is now the exponent, well, they're telling you the answer right here, that it's going to be 85. And down here they're showing you that if you took the function of this, and then we take the inverse of that, it ends up being 85. It's a little tricky, but let's go on to something that we can study in more detail. So here's a good little note here, a student note here, since this is equal to this log, is the inverse of this, the domain of the f is the range of G, and the range of f is the domain of G. Something to think about. Okay, so here is exponential function, where y equals ax, where a is your base, remember. And then if you switch the letters around, the x and y, you get the logarithmic functions. And here they're saying the domain is all real numbers, the range is all real numbers. Here the range is not including 0, but going to positive infinity. And the domain is, again, not including 0, but going to positive infinity. So the inverse is this, the logarithmic expression, and the inverse of this is our exponential function. The graph of x contains the point 0, 1. Remember, anytime we take the 0 power of something, it's 1. And this. And this, the graph of G contains the opposite, in the sense the inverse of this, and the inverse of that. Okay, again, you're not going to memorize this. Let's use some examples to illustrate it. Now I've taken a moment, I've paused the video to read this over, look at it, and again it would be making the tape too long if I did every single thing. But again, it's saying take these, find values. In a sense, you're making a t-chart, and this is what we have in our table here. Now when we plot the set of ordered pairs and connect the points with a smooth curve, you might say, oh, look at this. Similar to what we've done before. So the graph of y equals 5 to the x power, and keeping our axis of symmetry, y equals x, and these are just shown for reference, that this is the inverse in its logarithmic form of our exponential form. So we're sort of like overlapping what we did in section 2. Now, in most cases, again, when you do your practice, the graphs will be made for you and you just have to pick things out. But you need to know where your points came from. All right, common logarithms. I'll pause it here, and I would suggest you pause it as well as you look at what is written up here and look it over, read it over. So in summary of this, we would just say that we do have often the word common logarithms, that we're thinking of base 10. Mathematical theory here, we use base 10. There are other bases. The other common one is base 2, that is used for computing in the computers. There's other bases, and I recall in high school math when I would teach different bases, and we would work out things. I don't remember a lot of it, haven't used it lately. So when we see like log 17, this is a shortcut, which means log base 10, 17. Okay? And I could remember in high school using the tables, logarithmic tables in the back of our book, where it showed we had to get an approximation. Of course, we didn't have calculators. And I'm not sure how much we're going to be using calculators for in what we're doing here, but we'll see as we go on. Here's a little study tip: when a turn is trouble. Again, if you're turning pages in your textbook, or even as you look through this and you go to the next screen, as you scroll up, you lose what you have. So it's a good idea to write down the equation that you're working with, so if you do turn a page, you have a quick reference to what you're dealing with. Okay, now they are using calculators for this, and I'm going to have to see how we tie this in. So moving on, we see again equivalent equations. I'd put a star by that. We're repeating this a number of times. That m is equal to the log base a of x is equivalent to a to the m power equals x. So remember, we said that log was equivalent to the letter m, which is our exponent. So I would, again, write this down and keep in mind to what it is equivalent to. Do not forget this relationship. It is probably the most important definition in the chapter. Many times this definition will be used to justify a property we are considering. So in doing letter A, rewrite each equivalent exponential equation. So here we have it in log form, y equals that. Well, as we start to analyze it, what is our base? Our base is 3. We know that that is going to be raised to some log, which is the exponent, that will be equal to 5. So y then is our exponent. And there is our answer. All right, let's look at B. So as we look at B, we see our base here is going to be A. It's going to be raised to what exponent to equal 7? Well, our exponent here is a -2. Again, we're trying to show a strategy that you might use as a protocol to get these answers. So there is our example. Our base will be B to what exponent so that it will equal D. And our exponent is A. Okay, so these weren't too bad, and just tying in this expression or equation with this one. Again, you're looking for a strategy. This is what you want to put in your notes as you review your textbook or your PowerPoint slides or examples so that you have a reference on how to do some of this, and then you study it. Now, for these, we are going to rewrite an equivalent logarithmic equation back to what we just did, sort of the reverse. So here we have this. Now we're going to say our x, which is our exponent, is equal to the log of our base, which is 2, and of 8. And we already know what our x is going to be, right? What is it going to be? It's going to be a 3. So 2 to the third here, but they just want you to write it out to practice doing this. Now for this one, we know we're going to have our equivalent our exponent, I should say, -1 is right there, equals the log, our base is y, of 4. And then again, here we're going to have our exponent, which is b, of base A. So it's the log, b equals the log of A, equal to c. For some of you, it may be like learning a new language, trying to decode all of this stuff, but a systematic way of doing it and practice will bring you to, I think, mastery. That's what we're shooting for. So as we look at example 7, the first one here, what do we know? Well, we have a base of 2, which I'm going to put right there. Now we know it's going to equal x, which is right there. And what is our exponent? Well, our exponent is a -3. So now when we take 2 to the negative 3, which is 1 over 2 to the third. That gives us 1 over 8 for our first example. And then let's do the next one. Now in this next one, again, there's our example. We know our base is x. We know our exponent is going to be a 2. And we know the results will be a 16. So what do we have here? Well, to solve this, we can take the square root of this side plus or minus the square root of that side, remembering the principle of square roots from an earlier lesson, and we get x equals plus or minus 4. And that checks. It says one method for solving certain logarithmic equations and exponential equations relies on the following property, from which results from the fact that exponential functions are one-to-one. Again, going back to topic 2. The principle of exponential equality for any real number b, where b does not equal these, and we have this, is equivalent to x equals y. So they're asking us to solve this and then later solve this. So let's look at this. They're starting us off with a sort of easy one. So again, converting this log into exponential notation. So our base is 10. 10 to the x power equals 1,000. Well, we put the 1,000 into its exponential notation, 10 to the third. So now we have a 10 and a 10. Our bases are the same, so our exponents equal each other. Now that was an easy one. Again, you had to know that this was equal to that, and it does check. Now let's get to B. So here is our initial equation, log to base 4 of 1 equals t. Remember, t is our exponent, and that will result in 1 on this side. 4 is our base. So 4 to the t power. What did we say 1, what would be the exponent of 1? And we said that that one would have been to the 0 power. So our exponent then will be, well, I should say we have to make that 4 to the 0 power. There we go. So now our bases are the same. Our exponents now equal each other. Okay. Again, they have it worked out here. We're looking for a strategy to get to our answer. We had this. In order to get this to be the same base, we had to make that to the 0 power, which was equivalent to that. And then our exponents equal each other. Okay, that checks. Now, here they're giving us additional drill. Just some thoughts to think about, that when you have log base A is 1, The logarithm base, say, of 1 is always going to be a 0 because the exponent 0 has a base, whatever form it's in would be 1. And that's what we just saw an example of. And here are some others. Again, I'm not going to read everything. The tape is already 35 minutes. Wow. Okay, well, that wrapped it up. Again, you're going to have your practice. Take good notes, your homework log. Remember, a good homework log is 2 points added to your end of term grade. And good luck.